Hello everyone and welcome to another video. In this lecture, we will be discussing the metering and transport of fluids. Metering pertains to the measurement of flow rates of fluids flowing inside of a pipe, while transport of fluids pertains mainly to pumps and other fluid motive devices. Let's begin. For the first half of this lecture, we will be talking about the measurement of flow or the metering of fluids. When we try to measure the flow rate of a fluid inside of a pipe, and we know the cross-sectional area of the pipe by determining its diameter, we can also determine its velocity. So the measurement of flow not only pertains to flow rates like volumetric flow rate and mass flow rate, but it also pertains to the velocity or the average velocity of the fluid inside. We will be discussing the two most commonly used types of flow meters, namely the full bore meters and the insertion point meters. When we say full bore meters, these are the flow meters that consider the entire fluid flow or the whole fluid flow, meaning to say that all of your fluid would pass through the flow meter in order to register its velocity or its volumetric flow rate. Examples of these full bore meters are Venturi meters and Orifice meters. We will be deriving the governing equations for these two meters later. Another important type of flow meters are what we call the insertion point meters. The insertion point meters are vastly different from full bore meters in that the insertion point meters only consider one point of a fluid in motion. Usually, we are considering the center point of the flow because remember that for a fluid flowing inside of a pipe, be that may laminar or turbulent flow, the maximum velocity is captured at the middle of the pipe. That is the point that is farthest away from any solid boundary, that is the walls of the pipe. An example of an insertion point meter is a Pitot tube. This is pronounced as Pitot tube. We will also be deriving and discussing the governing equation for Pitot tubes. Let's start our derivations with the Venturi meter. This is what a Venturi meter looks like. So as you can see, we have the pipe here, diameter D1, and we have the throat of the Venturi with the diameter D2. By gradually decreasing the diameter of flow from the main pipe to the throat of the Venturi meter, we are increasing the velocity of the fluid and therefore we have a decrease in pressure. Now the decrease in pressure is notable in this manometer here, and by the way, we will be using the principles of manometry to determine the pressure drop for two different points. As you can see here, the pressure is greater on the pipe side before the fluid goes to the Venturi. When the fluid goes through the Venturi, its velocity is increased but its pressure is decreased, as you can see in the reaction of the manometric fluid here. Now for us to derive our governing equation for a Venturi meter, we can simply perform a mechanical energy balance on two different points of the Venturi. Now the most notable points that we should have is of course the point just before we enter the Venturi. We call this our point 1. And of course, another point is at the throats of the Venturi. We call this point 2. If we perform the mechanical energy balance along these 2 points, we can determine the velocity of the fluid flowing inside. Let's write our mechanical energy balance equation. That is delta P over rho plus delta U squared over 2gc plus delta Z, G over gc, plus F is equal to W. Now for this particular derivation, we are going to assume that there is no pumping work and there are no frictional losses. The frictional losses will be captured later in our final governing equation. We can also cancel our delta Z because there is no elevation change between points 1 and point 2. This is for a horizontal Venturi meter. If it is an inclined Venturi meter, then you have to include the value of delta Z into your derivation. Now let us direct our attention to the term delta U squared for a moment. Delta U squared means U2 squared minus U1 squared over 2gc. Remember that U sub 2 or U2 is the velocity at the throat of the Venturi, while U sub 1 or U1 is the velocity at the pipe or at the main pipe. So you have two choices here. Either you express our equation in terms of the velocity in the pipe or the velocity in the throat. That is a very important distinction to make because the velocities are very much different. It is higher in the throat and it is lower in the pipe. If you're asked for the velocity in the pipe, then you have to solve for U1. Okay, let's first solve for U2. How do we express U1 in terms of U2? Then we have to use the principle of the continuity equation. If you remember, the continuity equation states that the mass flow rate of the fluid going in is equal to the mass flow rate of the fluid going out. That's simply M1 is equal to M2. It's basically the law of conservation of mass. The mass flow rate is described as density times velocity times cross-sectional area. And that's also the same at the other side. If your fluid is a liquid, we can assume that the fluid is incompressible, and as such, we can say that the density is constant regardless of the flow. So with that, we can cancel density on both sides of the equation. You will be left with U1A1 is equal to U2A2. Again, for this illustration, we will be solving for the velocity at the throat. So that is U sub 2. So we have to express U1 in terms of U2. Rearranging this equation, we have U1 is equal to U2 times A2 over A1. But what is the cross-sectional area of the pipe and of the throat? Well, the cross-section are both circles, and the area of a circle is pi over 4 d squared. So we can actually express the ratio of the two areas with respect to the ratio of the two diameters. As such, we can say that A2 over A1 is equal to pi over 4 d2 squared over pi over 4 d1 squared. We can cancel pi over 4. We will be left with A2 over A1 is equal to d2 over d1 quantity squared. So we can write our expression U1 is equal to U2 times d2 over d1 squared. If we take the square of both sides of this equation, we get U1 squared is equal to U2 squared times d2 over d1 raised to the fourth power. And we can now substitute this back to our mechanical energy balance or the simplified MEB. We have delta P over rho plus U2 squared minus U1 squared is U2 squared times d2 over d1 raised to the fourth power all over 2gc is equal to 0. As you can see, our derived equation is now only dependent on delta P or the pressure drop across the pipe and the throats, rho or the density of the fluid, and the ratio of diameters d2 over d1 or that is the throats over pipe diameter. And we also have U2 or the velocity at the throats. Now to make this easier to track, let us use the subscript T to pertain to the throats. And let us use the subscript P to pertain to the main pipe. Applying these subscripts, we can rewrite our equation as delta P over rho plus factoring out U throats squared over 2gc, we would have 1 minus the ratio of diameter in the throats over the diameter of the pipe raised to the fourth power is equal to 0. To further simplify our equation, let us take a look at the term d throats over d pipe. The ratio of the diameters can actually be expressed as a single variable in order for us to save some space on our equation. So let us use the parameter beta to indicate that this is the ratio of the throat diameter over the pipe diameter. As such, this term here would become 1 minus beta to the fourth power. Rearranging the equation and simplifying, we can now solve for our throat's diameter, and that is equal to negative delta P times 2gc over rho divided by 1 minus beta to the fourth power. I simply transpose delta P over rho to the other side of the equation and then cross multiplied. And of course, we have to enclose all of this in a square root. This is our governing equation for the Venturi meter. With this simple equation, we can solve for the velocity of the fluid in the throat of the Venturi. What we only need is delta P or the pressure drop across the Venturi. We also need the density of the fluid and the beta or the ratio of diameters of the throats and of the pipe. As you can see in this figure, the throat diameter is smaller than the diameter of the pipe. As such, the value of beta is a decimal value, meaning it is always less than 1 because the throat is always smaller than the pipe. If beta is a decimal value, it's less than 1, then you take the decimal value, raise that to the fourth power, that would become even smaller. So there comes a point wherein 1 minus beta to the fourth will become very, very, very close to 1. But just to be safe, let us always evaluate this parameter. Now, remember earlier that I have mentioned that we can always incorporate the effect of friction into our Venturi meter. Granted, the effect of friction here is just small because in the Venturi meter, there is no sudden contraction and sudden expansion. This is actually a gradual decrease in diameter and a gradual increase in diameter. As such, that gives us a lesser amount of friction. Nonetheless, friction still does exist in this system, and we can characterize that with a simplified parameter C sub V. We can always multiply this by CV and then get the entire square root, negative delta P, 2GC, all over density times 1 minus beta to the fourth power. CV here is what we call the Venturi constant. The Venturi constant has a maximum value of 1, and its usual value is around 0.96. So for a well-built Venturi, you can use a value of CV between 0.96 to 0.98. It all depends on the calibration of the Venturi. This also factors out the effects of friction in our system, because any value of the Venturi constant less than 1 indicates that our system is not perfect. As such, there are losses due to friction. Although if we have a CV that is equal to 0.96, we could say that that is a well-built Venturi because the losses due to friction are just small. Now that we have our governing equation for the Venturi meter, how do we determine the actual velocity of the fluid in the throats and in the pipe? Notice that in our final equation, we have the value delta P. That is the pressure drop between the points 1 and 2. How do we determine our delta P? Let me erase some of this first. You need to refresh your memory on our lesson on manometry because in this case, we are using a U-tube manometer that indicates the pressure difference between points 1 and points 2. As you notice, we can easily determine delta P by our simple manometric equation. You can go back to our lesson in manometry and try to derive our pressure drop for points 1 and 2, but I will write it here that the pressure drop or negative delta P, this is P1 minus P2 is equal to the density of the manometric fluid, let's assume that that is mercury, minus the density of the fluid inside, let's say for example water, ethanol, or any other fluid that is less dense than the manometric fluid, multiplied by G over GC times H, wherein H is the difference in the heights of the arms for points 1 and points 2 of the U-tube manometer. If we substitute this equation to our governing equation for the velocity in a Venturi meter, we get the velocity at the throats is equal to CV multiplied by the square root of 2 times density of the manometric fluid minus density of the flowing fluid multiplied by G multiplied by H divided by the density of the fluid times 1 minus beta to the fourth power. Please take note that there are two different densities in this case. That's the density of the fluid flowing inside the pipe and the density of the manometric fluid. Do not confuse between the two densities. Also, you cannot neglect the density of the fluid in the numerator here because most often for liquids, their density is large enough that if you omit this term here, there will be large errors in your throat velocity. Now that we have determined the velocity of the fluid at the throats of the Venturi, how does this translate to the velocity of the fluid at the pipe? Well, you simply just have to go back to our continuity equation, and this is our final derived equation from the continuity equation. That is, the velocity at the pipe is equal to the velocity at the throats times the ratio of the diameters. So we can rewrite that as velocity in the pipe is equal to velocity in the throats multiplied by beta squared. Remember that beta is the ratio of the diameters at the throats and at the pipe. So these two governing equations are all that you need in order for you to determine the velocity of flow of the fluid. And that is the main point of using a flow meter to determine the velocity of a flowing fluid. Okay, let's try to solve an example. A well-designed Venturi meter having a throat diameter of 38.9 millimeters is installed in a line having an inside diameter of 102.3 millimeters. It meters water at 30 degrees Celsius. The measured pressure drop across the Venturi is 156.9 kilopascals. Calculate the volumetric flow rate of water. Let us remember one of our governing equations for Venturi meters, that is, the velocity at the throats is equal to CV multiplied by the square root of negative delta P times 2GC divided by density of the fluid times 1 minus beta to the fourth power. I am using this form of the equation because we are already given our pressure drop. That's 156.9 kilopascals. If you are not given this pressure drop, then you have to use the other form of the equation wherein delta P is expressed in terms of rho GH. Let's solve for the value of beta. Beta in this case is equal to the diameter at the throat over the diameter of the pipe. Substituting from the given, that would be 38.9 millimeters divided by 102.3 millimeters. That is the throats over the pipe diameter. Our beta is equal to 0.3803. We are going to use that later. Our other given from the problem is first, the Venturi meters water at 30 degrees Celsius. The density of water at 30 degrees Celsius is around 995 kilograms per cubic meter. So we're going to use that later. This is the density of the working fluid, not to be confused with the density of the manometric fluid. As mentioned earlier, we have our pressure drop, 156.9 kilopascals. You simply have to convert this to pascals so that there would be no conflicts in the units. Another given that is hidden in the problem is this one, a well-designed Venturi meter. Whenever we say that a Venturi meter is well-designed, you can simply assume that the CV value of that is 0.96. This comes from many papers describing the calibration of Venturi meters, and they have determined that the average CV ranges from around 0.96 to 0.98. So we're just going to use 0.96. And with that, we are ready to substitute everything to our governing equation. That would simply be CV 0.96 multiplied by the square roots of the ratio pressure drop. Remember that pressure drop is negative delta P, okay? You can think of this parameter as one whole parameter with the negative being included inside of the parentheses. With this, we say that negative delta P is equal to 156.9 kilopascals. This is pressure drop. You are not supposed to remove or misplace this negative sign in front of the delta P. Okay, moving back, our pressure drop is 156,900 pascals times 2 GC, so that's simply times 2 for SI. The density of the fluid is 995 kilograms per cubic meter multiplied by 1 minus beta to the fourth. That would be 0.3803. If you want to be more exact, then you can simply directly substitute the value of beta, that is the ratio of 38.9 over 102.3. And this is raised to the fourth power. Our answer, the velocity at the throat is equal to 17.23 meters per second. This is not yet our final answer because we are asked to calculate the volumetric flow rates of water. The volumetric flow rate, if you remember, is equal to the velocity multiplied by the cross-sectional area of the conduit. In this case, we have two velocities and two cross-sectional areas. It is important that you do not mix the velocities and the cross-sectional areas of the pipe and of the throats. Since our fluid is incompressible, we can write this relationship such that our volumetric flow rate can either be the velocity at the pipe multiplied by the cross-sectional area of the pipe, or this could also be equal to the velocity at the throats multiplied by the cross-sectional area of the throats. You can never mix these two definitions of velocities and cross-sectional areas, okay? So you cannot say that this is also equal to the velocity at the pipe multiplied by the cross-sectional area at the throats. This is wrong, okay? So let us just stick with these two options. Now, the question is, which among these two should we choose? Well, it depends on what we have determined. We have determined the velocity at the throats, and we also know the diameter at the throats, so we can use this second one. Let's solve this as Q is equal to velocity at the throats multiplied by the cross-sectional area at the throat. So this is velocity at the throat times pi over 4 times diameter of the throat squared. Substituting, the velocity at the throat is given here, 17.23 meters per second, multiplied by pi over 4 times our diameter squared. Our diameter is 38.9 millimeters in the throats, divided by 1,000 to make it meters, and this is squared. Our volumetric flow rate is equal to 0.0205 cubic meters per second. We use the unit cubic meters per second because everything that we have solved uses standard SI units. and that is how we solve problems involving Venturi meters. Let's proceed. The orifice meter is another type of a full-bore meter similar to a Venturi. Based on this illustration of an orifice meter, you can kinda see what are the differences and similarities with Venturi meters. First, for the similarities, both the orifice meter and the Venturi meter rely on a constriction or a decrease in the flow area to register a pressure drop and to register a difference in velocities. And with that, you can also see their main difference. For the Venturi meter, the decrease in area is gradual, while for an orifice meter, the decrease is drastic. This sudden decrease in area and the sudden increase in area of the flow, as you would imagine, would result to a large amount of energy loss due to friction. So we can already predict that the orifice constant, in contrast with the Venturi constant, is smaller in value. Since the orifice meter is very similar in operation with the Venturi meter, it is no surprise to us that the working equation for an orifice meter is the same as that of a Venturi meter, with only one different parameter. So we write the velocity in this case as U sub O, indicating the velocity at the orifice, and this is equal to C sub O, or the orifice meter constant, multiplied by the square roots of the pressure drop, negative delta P, times 2gc, divided by density of the fluid times 1 minus beta to the fourth. It's the same equation. Okay, the beta in this case is defined as the diameter of the orifice over the diameter of the pipe. This is our orifice. The orifice is the small opening that restricts the flow of the fluid into that small area. The pressure drop that registers here is due to the restriction in the flow area. Now you might be asking, what is the advantage of using an orifice meter versus a Venturi meter? The number one advantage is that orifice meters are very easy to install because they are just a plate with a hole in the middle. So you can just insert this relatively easier compared to a Venturi meter because Venturi meters are quite bulky because remember, you have to allow for the gradual decrease and gradual increase in flow area. Well, the main disadvantage of an orifice meter, to contrast that, is that it generates a lot of frictional losses. For orifice meter, there is a parameter that we call impermanent losses. And those impermanent losses are energy loss of the fluid that is due to the sudden decrease in flow area. Okay? But in principle, they have the same working equation. Now, let's talk about the value of C sub O, or the orifice coefficient. For the Venturi meter, CV is equal to 0.96 for a well-built Venturi meter. For an orifice meter, the value of CO changes with regards to the velocity of the fluid flowing. And that creates a paradox because for you to be able to determine the velocity of the fluid flowing inside of an orifice meter, you need to determine the value of CO, or the orifice coefficient. But the orifice coefficient changes its value with regards to the velocity of the fluid flowing inside of the pipe. So there exists a codependency between the velocity and the orifice coefficient. This often leads to a trial and error solution for flows that are not turbulent. For highly turbulent flows, we can assume an initial value of CO as 0.61. This initial value of CO will allow us to determine the velocity at the orifice and of course the velocity at the pipe. You can always check if the value you assumed for CO is valid. You can only use CO is equal to 0.61 if the Reynolds number at the orifice is greater than 10 to the fourth power or 10,000. Okay, the Reynolds number at the orifice is simply the diameter of the orifice, velocity at the orifice, density over viscosity. And as you can see, the Reynolds number is still dependent on the velocity at the orifice, which is dependent on the orifice coefficient. So this is why we have to check. If it is less than 10 to the fourth, then you have to choose a different value of CO, and we have a graph for that. This is the graph that we normally use to determine the coefficient of discharge C, or CO, that is the orifice coefficient. As you can see in our x-axis, we have our Reynolds number values. This Reynolds number are for the orifice of an orifice meter. If you take a look at 10 to the fourth power or 10,000, beyond this range, all of the curves converge to one point. This point is 0.61. Right? That's why it is safe to assume that the initial value of CO is 0.61 upon the assumption that the flow is turbulence enough, that is Reynolds number greater than 10 to the fourth power. If it is not turbulent enough, or if the Reynolds number is less than 10,000, then you would need to use this graph to determine the orifice coefficients. First, you have to determine the value of the Reynolds number, that is d u rho over mu, all at the throat. And you also have to determine your beta. These are the different values of beta. In here, it is stated as a diameter ratio. So if your beta is 0.8, for example, then we have to use this topmost curve. Let's say, for example, your Reynolds number is 1000. So 10 raised to the third power. You take a look at the intersection of that curve with the diameter ratio 0.8. The intersection points us to the value 0.95 as our discharge coefficient. Okay, that is how you use this graph. Now remember, we only have to use this graph if the Reynolds number is less than 10,000 at the orifice. But for the first case solution, you can always assume that the orifice coefficient is 0.61. Let's try to solve an example. A sharp-edged orifice having a diameter of 0.0566 meters is installed in a 0.1541 meter pipe through which oil having a density of 878 kilograms per cubic meter and a viscosity of 4.1 centipois is flowing. The measured pressure difference across the orifice is 93.2 kilonewtons per square meter or kilopascals. Calculate the volumetric flow rate in cubic meters per second. Again, let us recall our governing equation for an orifice meter. That is, the velocity at the orifice is equal to the orifice coefficient CO multiplied by the square root of pressure drop, negative delta P, times 2gc, divided by the density of the fluid times 1 minus beta to the fourth. We are basically given everything here. We are given the diameter at the orifice and the diameter of the pipe. So we can substitute that directly into our beta. What we don't have here is our value of C sub O, or the orifice coefficient. As I've mentioned earlier, we can validly assume that our initial CO is 0.61 and then later check if our Reynolds number is really greater than 10,000. Okay, so let's first assume that. Our first assumption, CO is equal to 0.61. Let us substitute our given. That would be 0.61 multiplied by the square root of pressure drop, 93,200 pascals times 2gc divided by density of the fluid is given, 878, multiplied by the quantity 1 minus beta. Our beta is 0.0566 divided by 0.1541. And this quantity is raised to the fourth power. The velocity at the orifice, as we have solved, is 8.97 meters per second. We can use meters per second because we are using all standard SI units. Now to check, we have to determine the Reynolds number at the orifice. That would be diameter of the orifice, velocity at the orifice, density over viscosity of the fluid. The viscosity of our fluid is given as 4.1 centipois. You can always convert this to millipascal seconds. You simply remember that 1 centipois is equal to 1 millipascal seconds. Therefore, our viscosity is 4.1 times 10 raised to negative 3 pascal seconds. Substituting, we have the velocity at the orifice, 8.97, multiplied by the diameter at the orifice, 0.0566, times the density, 878, divided by the viscosity, 4.1, times 10 raised to negative 3. Our Reynolds number at the orifice is 111,000, or this is equal to 10 raised to the fifth power, which is greater than 10 to the fourth power. That means that 0.61 as our initial assumption for CO is validated. Since our assumption is now validated, we can use this value of the velocity at the orifice. And again, we are asked to solve for the volumetric flow rates of the oil. The volumetric flow rate is equal to the velocity at the orifice multiplied by the cross-sectional area of the orifice. This is equal to UO times pi over 4 times diameter of the orifice squared. Substituting, that is 8.97 meters per second multiplied by pi over 4 times diameter of the orifice, 0.0566 squared. Our volumetric flow rates in this case is 0.0226 cubic meters per second. That's our final answer. Okay, so the treatment for a Venturi and Orifice meters are basically similar except for their coefficients. For a well-built Venturi, you can use 0.96, while for an Orifice meter, we first have to assume that the value is 0.61 and then later check if that is valid. If your Reynolds number here is less than 10 to the 4th power, then you have to consult the graph and determine the real value of the Orifice coefficient. Okay, and that is how full bore meters work. Let us now proceed to insertion point meters. As mentioned earlier, insertion point meters only measure the velocity of the fluid at one point. And a good example of insertion point meters are Pitot tubes. This is an example of a Pitot tube. As you can see, it's simply a U-tube manometer wherein one of the openings of the manometer is directed at the center of the flow in the pipe. So you are only measuring the velocity of the fluid at this point, at the center point in the pipe. And we can simply use some correlations to determine the average velocity in the pipe. Now, our governing equation for a Pitot tube is quite different from that of the Venturi or the Orifice meters, but the derivation is the same. We are going to use the mechanical energy balance equation. So, for our derivation, let me name this point as point 1, and this point right here is point 2. Now, the important thing to remember here is that point 1 sits exactly at the mouth of the tube of the manometer, that is in point A here. Okay? At this point, the velocity of the fluid is actually 0. That is because the fluid element here is pushing against the liquid inside of this tube in the U-tube manometer, and it is pushing against this manometric fluid. And the practice of manometry can be applied for fluids that are not moving or are not flowing. In this case, the manometric fluid is not moving, so we can also say that the fluids attached to this are also not moving. That includes point 1. In contrast, our point 2 here consists of the fluid that is flowing inside of the pipe. So we can say that U2 is the velocity in our pipe, but this is at the center only. And as we have learned for fluid flowing inside of a pipe, since the center point is the point that is farthest away from all of the solid boundaries, then we can also say that U2 is our maximum velocity. The maximum velocity cannot be used for our determination of the volumetric flow rate or mass flow rate because we first have to convert this to average velocity. For this derivation, again, we start with the mechanical energy balance equation. That's delta P over rho plus delta U squared over 2gc plus delta Z G over gc plus F is equal to W. Again, we can cancel W because a pump is not involved between points 1 and 2. We can also first cancel F, that is the contribution of frictions, and we can just add that later with our coefficient of the Pitot tube. We can also cancel our delta Z because there is no change in elevation between points 1 and points 2. And our delta U squared can be simplified to just be equal to U2 squared. Right? Because U1 is equal to 0, therefore U1 squared is equal to 0. Therefore, your mechanical energy balance simplifies to delta P over rho plus U2 squared over 2gc, that's equal to 0. Remember that U2, again, is the velocity at the center of the pipe, and this is the maximum velocity. Therefore, rearranging this equation would give us U maximum is equal to negative delta P over rho times 2gc. And this is all under a square root. This is our governing equation for the maximum velocity of a fluid flowing inside of a pipe. However, like what we did earlier, we have to insert our correction factor for the Pitot tube. So we can say that our final equation is U max is equal to Cp times the square root of the pressure drop, negative delta P, times 2gc over density of the fluid. Cp, in this case, is the Pitot tube coefficient. For a well-built Pitot tube, you can take this coefficient as around 0.98. Okay, this is for a well-calibrated and well-constructed Pitot tube. As you can see, our equation here is much simpler than that involving Venturis and orifices because there is no change in cross-sectional area of the flow. For Pitot tubes, we are just relying on the stagnation of the fluid at point 1 to register a difference in pressure in our U-tube manometer. And as always, the pressure drop can be expressed in terms of rho GH, that is the density difference between the manometric fluid and the governing fluid, times G over GC times H. Now let's talk about the conversion between maximum velocity and average velocity. As we have established, the maximum velocity cannot be used to determine the volumetric flow rates and the mass flow rates. We first have to convert the maximum velocity to average velocity. Whenever we are solving for the volumetric flow rate, for example, and this is velocity times the cross-sectional area, the velocity here is actually an average velocity. It is never a maximum velocity. Because if we use the maximum velocity for this equation, then you will be off significantly in your determination of the volumetric flow rates. So how do we determine the relationship between average velocity and maximum velocity? We look at another graph. This graph relates to us the ratio between average velocity and maximum velocity on the y-axis with regards to the maximum Reynolds number in our bottom x-axis. The way on how we use this graph is you first determine the maximum Reynolds number, that is diameter of the pipe times maximum velocity times the density of the fluid over its viscosity. When you have the value of the maximum Reynolds number, you can project upwards towards this curve here with the arrow pointed down, and the intersection of between those 2 points would determine your ratio of the velocities. Okay, we will use this graph in our example. Let's try to solve this problem. A Pitot tube is used to measure the air flow in a circular duct 600 millimeters in diameter. The flowing air temperature is 65.6 degrees Celsius. The Pitot tube is placed at the center of the pipe and the manometer reading is 10.7 millimeters of water. A static pressure measurement at the position of the tube reads 205 millimeters of water above atmospheric. We are to calculate the maximum velocity and the volumetric flow rate of the air flowing inside of the duct. First, let us recall our governing equation for Pitot tubes, that is the maximum velocity is equal to the coefficient of the Pitot tube times the square root of pressure drop, 2gc, over the density of the fluid. In this case, our fluid is a gas, that is air. The density of air can be solved by the equation Pm over RT, assuming that air behaves ideally. In this case, the pressure of the air can be determined as the static pressure measurements at the position of the Pitot tube, that is 205 millimeters of water. We just have to convert this to pressure units. While the manometer reading 10.7 millimeters of water tells us that our manometric fluid is water. Okay, so we are to use the density of water. As such, our pressure drop in this case, negative delta P, would be equal to the density of water, our manometric fluid, minus the density of air multiplied by G over GC times H. H in this case is 10.7 millimeters. Okay, let's first calculate the density of our fluid, which is air. For us to convert the 205 millimeters of water above atmospheric, this is where our manometric equation would be useful. That is, pressure is equal to rho G over GC times H. Do not get confused with this equation because the density pertained here is the density of water, because water is our manometric fluid. For that, we can now substitute our given. Let's say that the density of water is 1000 kilograms per cubic meter. We multiply that with G over GC, 9.81, and that is multiplied with H. Our H is 205 millimeters. Converted to meters, that is 0.205. Our pressure is equal to 2011.05 pascals. Remember that this pressure that we solved is a gauge pressure. We know that this is gauge pressure because of the wording of the problem, 205 millimeters of water above atmospheric pressure. So for us to be able to use this pressure for our equation for density, we have to convert this to absolute pressure. To convert this to absolute pressure, we simply add 101,325 pascals. The absolute pressure of air is 103,400 437 pascals. We can now substitute this to our density for air, that is pressure, 103,437, times the molecular weight of air, 0.029 kilograms per mole, divided by R, 8.314 joules per mole per Kelvin, divided by the absolute temperature, 65.6 degrees Celsius plus 273.15. The density of our air is 1.07 kilograms per cubic meter. This is the density that we're going to use for our calculation of maximum velocity. Okay? Do not confuse the densities in here. For our calculation of the gauge pressure, we use the density of the manometric fluid. In this case, that's water. And for our maximum velocity equation, we use the density of our working fluid, which is air. Let's now solve for the maximum velocity. Umax is equal to Cp. Our Pitot tube coefficient, we can use 0.98 for a well-built Pitot tube. We multiply that with the square root of, first on the numerator, that is pressure drop. We characterize that as the density of water, 1,000 kilograms per cubic meter, minus the density of air, 1.07, multiplied by G, in this case 9.81, multiplied by H, or the manometric reading from the problem, that is the 10.7 millimeters of water. Converting to meters, that is 0.0107 meters. And on the denominator, we have the density of our fluid, which is air, 1.07 kilograms per cubic meter. Our answer for U maximum is equal to 9.7 meters per second. This is the velocity of air at the center of the conduit. Now, as I've mentioned earlier, whenever we are solving for a volumetric flow rate, you cannot use the maximum velocity. So let us go to our graph and determine our ratio. Again, for this graph, we first have to determine our Reynolds number maximum. We calculate that as the diameter of the pipe is 600 millimeters, that is 0.6 meters, multiplied by the maximum velocity that we have determined, 9.7 meters per second, times the density of air, 1.07, divided by the viscosity of air. The viscosity of air can be taken as 2.03 times 10 raised to negative 5 pascal second. Our Reynolds number maximum is 307,000, or this is 3 times 10 raised to the 5th power. If you take a look at our graph, this is 1 times 10 raised to 5, 2 times 10 raised to 5, and 3 times 10 raised to 5. This is our sweet spot. We project this upward, and we have this intersects with our curve, and then the intersection will be read on the y-axis as our ratio of the average over maximum velocity. I will take that as 0.84. If our ratio of average to maximum is 0.84, we simply multiply our maximum velocity, 9.7 meters per second, with 0.84 to get the average velocity. Our average velocity is equal to 8.15 meters per second. This is what we are going to use to calculate for the volumetric flow rate. Our volumetric flow rate is equal to, again, U times A. This is U average. Let us substitute everything we know. Our average velocity is 8.15 or 8.148 meters per second. We multiply this with pi over 4 times the diameter of the conduit, 600 millimeters or 0.6 meters squared. We have the volumetric flow rate, 2.31 cubic meters per second of air. This is our final answer. Even though our governing equation is quite different, the solution is similar. We just have to consult a graph to convert from maximum velocity to average velocity. Now, before we close this lecture, let me go back to the graph. If you take a look at this graph, at the initial portion, you have this horizontal line that pertains to the ratio equal to 0.5. That is, the average velocity over maximum velocity is equal to 1/2. And this is actually the regime of laminar flow. For laminar flow inside of a pipe, the average velocity is always half of the maximum velocity. If you take a look at the reading of the Reynolds number, 10 raised to 3, this is 1,000, this is 2,000, and at 2,100, or the upper limit of laminar flow, beyond this, the ratio is no longer 0.5. It drastically increases for this transition region, and for the turbulent region, it is steadily increasing. This is further proof of the differences between laminar and turbulent flow. The difference is very pronounced in this case. And with that, we end our discussion on flow meters. Thank you for listening, and as always, keep safe.